Another hello from West Virginia or somewhere. I don't know where. But what I do know is that I have Joke of the Day because I know you're waiting for Joke of the Day. I know it's your favorite part of the day. And are you ready? Because this is a good one. What do hockey players, what type of tea do hockey players drink? What type of tea do they drink? Penalty. That's a great one. And the other thing that is great is rationalizing a denominator. So we're going to take a look at rationalizing a denominator because you cannot have a radical in the denominator of a fraction. Now, it's not like having a zero in the denominator of a fraction. You know that if you have a zero in the denominator of your fraction is considered to be undefined. Undefined means that it does not exist. Like literally, it's not even there. And we need our fractions to exist, so you really, truly cannot have a zero in the denominator of your fraction. But this idea of not being able to have a radical in the denominator of a fraction, okay, it shows up. So therefore, having a radical in the denominator doesn't make it not exist. It still exists, it's just what we call bad form. So to fix the form, what we do is this process called rationalizing the denominator. Now, in order to rationalize that denominator, here's the process. You multiply your numerator and your denominator by a number that will create a perfect square. Because if you have a perfect square, can you take the square root of it? Yeah, you sure can. Let's think about it. Perfect squares. 9 is a perfect square. Because what's the square root of 9? What would you multiply by itself to create a 9? Yeah, a 3. 49 is a perfect square because what would you multiply by itself to create a 49? 7. So 7 is the square root of 49. 100 is a perfect square. What's the square root of 100? What would you multiply by itself to create 100? 10. So the idea is I need a perfect square in the denominator of that fraction so that I can take its square root and get rid of that radical. So let's take a look at these 3 examples. In each of them we're going to rationalize that denominator because as you can see here, I've got a radical in the denominator. Not cool at all. I'm going to get rid of it by rationalizing that denominator. Now this is all based on that product rule. Remember the product rule said that if I have 2 radicals that are being multiplied together, what I can do is I can take those numbers that are underneath the radicals and I can multiply them together. So I'm going to take this 10 that's underneath the radical, I'm going to multiply it to whatever that number is, and when I multiply these together, I want a perfect square so that I can take the square root of it. So if that's the case, what probably should I multiply to this 10? Yes, a 10, because 10 times 10 is how much? Yep, 100. And what's the square root of 100? Yeah, 10, because I would multiply 10 times 10 to create 100. And voila, ta-da! The radical is gone. So that's the beauty of it. I need to multiply this denominator by a square root of 10 because the product rule said, okay, now that I've got 2 radicals here and I'm multiplying them together, I can take these 2 numbers that are underneath the radicals, put them together under one big radical, multiply them together, and the voila beauty is that creates a perfect square and take the square root of it. But you know that whatever you multiply on a denominator, you have got to multiply up on a numerator because you don't want to change the value of the fraction. Right here, square root of 10 over square root of 10 is how much? Yeah, it's just a 1. And whenever you multiply something by a 1, do you change value? No, you do not. And all I'm trying to do here is fix the form. I'm just trying to change the way it looks. I don't want to change its value at all. So when I multiply down on a down on a denominator, I have got to multiply up on a numerator. Now, when I go multiplying here, notice the 18 does not have a square root. So therefore, I cannot put them together underneath one big radical, nor can I take the 10 outside of that radical. They're going to have to just sit beside each other. I think of the radical kind of like a tent. Both these guys are underneath the tent, so they can play together under the tent. This guy's under the tent, but that guy's not. So they can't play together. This guy's got to sit outside the tent. He can't get inside the tent. If they're both outside the tent, they can play. If they're both under the tent, they can play. But if one's out of the tent and one's under the tent, they can't play together. And they're just going to sit beside each other like this. But sitting beside does indicate multiplication. So I have an 18 square root of 10 on that numerator all the way across. And now remember the quotient rule said, kind of like the product rule, said if 2 numbers are under a radical, then I can put the two numbers and divide them underneath one big radical, but only if they are both under the radical. Notice these tens are not both under the radical. It's that tent idea. He's under a tent, he's not under a tent. So these two cannot play together. But he's not under the tent, he's not under the tent, those two can play together. So I'm going to look at this part of it, and I'm just going to try to simplify that fraction, 18 over 10. What number will go into both 18 and 10? Well, yeah, that's a 2. 2 goes into 18 9 times, 2 goes into 10 5 times, and so my simplified fraction is 9 square root of 10 over 5, and once again, do not take that 10 and divide it by 5. The 5 is not underneath a radical. Quotient rule says, oh yeah, if they're both under a radical, go for it. But these are not both under a radical. The tent, he's outside, he's inside, can't play together. So this is as simple as it will get. 9 square root of 10 over 5. All right, let's try just a couple more just to make sure we're really good at this. Notice in this example, I can take a 64 and divide it by 7, but if I do, I'm going to get some crazy nasty decimal. I do not want to deal with that. So instead what I'm going to do is I'm going to use my quotient rule that not only said can I take two radicals, that one's on the numerator, one's on the denominator, put them together underneath one big radical, but I can also split them up if they're underneath one big radical. So I'm going to take that square root, I'm going to send it up there to that numerator, I'm going to send it down here to this denominator, and the square root of 64 is 8. So I have 8 over square root of 7. Oh, there it is. I have a radical in the denominator. So to rationalize that denominator and get that radical out, I need to multiply that denominator by something that will create a perfect square. Knowing that I need to multiply it by a radical, 7 times what will create a perfect square? Well, 7 times 7 will create a 49, so I'm going to multiply that by square root of 7 so that I get square root of 7 times 7, 49, and the square root of 49 is 7. Ta-da! The radical's gone. Beautiful thing. And like we said before, what we multiply on a denominator, we have got to multiply up on that numerator. Now, please don't get confused because everybody goes, oh wait, didn't you say when you multiply fractions you cancel those diagonals? Why are we not canceling on these diagonals right here? Well, you could, but notice if you do, you're going to get back to an 8 over square root of 7. It's going to send you right back where you were. You don't want to do that. You want to get rid of the radical in the denominator. So this time, don't cancel on those diagonals. Let's just go ahead and shoot straight across. But across here, once again, outside the tent, inside the tent, they can't play together. He cannot creep inside the tent. He can't escape the tent. So they're just going to sit beside each other, 8 square root of 7, all the way across. And just like we said before, quotient rule says, okay, if this square root of 7 is underneath a radical, they can play together and you can cancel the 7's out. But he's outside the tent, he's under the tent. They cannot play together. So the only thing I can do at this point is just look at this fraction here because the 8 and that 7 are both outside. Will that simplify? No, there is not a number that will go into both 8 and 7, so this is as simple as it will get. And like I keep saying, don't worry about turning them into mixed numbers. At this point in the game, we like these impropers. We're totally cool with impropers. But always simplify a fraction if you can. All right, let's take a look at this last one. That may look familiar. We had one like this before. And before we said what we're going to do is we're going to go ahead and put them together according to that quotient rule because they're both underneath that radical. And we said the reason we're going to do this is because at that point in time, even though this turned into a 10x squared, because I know the square root of 100 is 10, I know the square root of x to the 4th is x squared, but at that point in time we had no idea what to do with this. So what we did at that point in time is we said let's just go ahead and take that 100 and divide it by 5. And let's take this x to the 4th and divide it by x. And if you recall, what we got out of that one was a 2x square root of 5x is what we got. Now, we now know what happens when we've got a radical in the denominator. So at this point, we could go ahead and say, well, I know the square root of 100 is 10. I know that I would multiply x squared times x squared to get an x to the 4th. So the square root of x to the 4th is x squared. Now I know how to rationalize that denominator. So what I'm going to do is I'm going to multiply that denominator. I'm going to get a square root in there, and I'm going to multiply this 5x by something that will create a perfect square so I can take the square root of it. Well, what would I multiply to a 5 to create a perfect square? Sure, let's multiply by 5. Because 5 times 5 is going to give me 25. And I know that the square root of 25 is just a 5. But now I still got this x under here. So what would I multiply to the x to create a perfect square? Well, how about an x? Because x times x will give me x squared. And what's the square root of x squared? Just an x. So I have a 5x in that denominator, but the beauty is that I don't have a radical in the denominator. But when I multiplied on the denominator, I have to multiply on the numerator. So I'm going to take that numerator and multiply it by square root of 5x all the way across. And like I said before, outside the 10, inside the 10, can't do a thing with it. So I have a 10x squared, square root of 5x, carried all the way across. And so when I carry it down here, 10x squared, square root of 5x, remember, he cannot go inside that 10, but he can cancel with this. 10 divided by 5 is 2. X squared divided by x is x. So I do end up with a 2x square root of 5x, just like I got the previous time. So I hope that helps with the idea of rationalizing a denominator. Now do notice that these denominators are sort of kind of simple. I know they feel complicated, but it's a single term in that denominator in each one of these cases. So in the next video, we're going to look at what happens when you have a couple of terms in the denominator, like maybe a couple terms being added or a couple terms being subtracted, and there is a radical in that denominator. What am I going to do? How am I going to get that radical out of there? Called using a conjugate. But I hope this helps with the basics of rationalizing a denominator. Have a great day.